Welcome to Wildcat Science with Mrs. Haugo. This is Chemistry, Chapter 12, Section 1. And so Chapter 12 is on reaction rates and equilibrium, and Section 1 focuses on reaction rates. So some reactions happen very quickly, like rocket fuel combusting, whereas other reactions happen very slowly, like iron oxidizing, like if you left your bike chain out this winter. And so they're both chemical reactions, but one happens very fast and the other one happens slowly over days or weeks or even months. Looking at our book, and if you would like to follow along, we're on page 366 in our book, chapter 12. Some things you'll be able to answer at the end of this chapter. What determines how rapidly chemicals will react? Do chemical reactions stop after a period of time? And can chemical reactions go backward, and can they be reversible? And we looked at some fast reactions like rocket fuel, and slow reactions, so the bread aging and the mold growing on the bread. Also, there's a nice chemical reaction here. You can see we have blue dye structure right there. And then when bleach is added over time, over 4 minutes, you can see that a chemical reaction. What does the speed of the chemical reaction depend on? Well, one thing it depends on is the concentration. Increasing the concentration increases the reaction rate. Looking on the next page, we can see magnesium in 1 molar HCl is reacting a little bit, but a magnesium strip in 6 molar HCl is reacting quite a bit faster. The reaction rate also depends on the temperature. Increasing the temperature will increase the reaction rate. That's why we will heat a lot of our chemical reactions. If you remember when we did if you were here freshman year when we did copper and we heated it to make it copper oxide, if we hadn't heated it, eventually some of it would have turned into copper oxide, but you'd probably be graduated by that time. And surface area. Increasing the surface area increases the reaction rate. And so a lot of times this is why we will cut things up or mash them into a powder so that there is more surface area for that chemical to react. Also, a catalyst. Adding a catalyst will speed up dramatically the speed of the reaction. So the presence of catalyst dramatically speeds up most reactions. And indeed, a lot of reactions wouldn't occur if there was not a catalyst, or they wouldn't occur at a rate that would be helpful to anybody. The question is, what is a biological catalyst? If you said it is an enzyme, you are right. And so enzymes speed up reactions in our body, and if we didn't have enzymes, the reactions would happen so slowly that we just wouldn't be able to live. So, what is reaction rate? The reaction rate is the speed at which chemical reactions occur, and it's measured by the change in concentration of the reactant, or you could do a product, per unit time. So we have a chemical reaction occurring, and then we measure the concentration of the reactant at the beginning, and then maybe in the middle and at the end, and that determines our reaction rate, how fast the concentration of the reactant is changing. Let's look at a diagram of this. So you can see at time 0, we're starting with reactant A, and we have 100% of reactant A. After 10 seconds, there's been a chemical reaction, and some of my reactant A has chemically changed into product C. And then you can see after another 10 seconds, so 20 seconds total, more product C has been produced, and there's less of product A. However, in the first 10 seconds, we had 1, 2, 3, 4 product C's, and then if it was a constant rate, we'd have 8 product C's after 20 seconds, and we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So it's not quite constant. And let's look at this diagram also. So we have the first part of the reactant is fast, and the concentration of the reactant A is going down pretty quickly because it's being converted into, it's chemically reacting and becoming product C. And then as there's less and less of the reactant, it takes longer for the rest of the reactant to react. And the opposite is true for the product. The product begins forming really fast, and then a few more are produced as time goes by. So let's take a look at this equation. You don't have to write this down, but the rate is equal to the change in concentration in molarity over your change in time. Looking at the diagram on page 373, this shows a good example of the collision theory, which is that products have to be formed when the reactants hit together. And they do have to be hit at the right speed and in the right position. That's a lot like playing pool, where if you hit the white ball, let's say you're going after the orange ball, and you hit it straight on with enough energy, it'll go into the pocket. However, if you're a little bit off and you hit it on one side, it's going to go in another direction and you will have an unsuccessful collision. You won't get the pool ball in the pocket, and that's just like molecules. You have to hit them in the right place with the right energy for there to be a chemical reaction. Coming back, please write this down. Molecules must hit each other with enough energy at the proper angle for bonds to be broken and reformed. And that minimum amount of energy is called the activation energy. And before we're done, I want to practice reading reaction profiles. So let's do that. So looking at this diagram on page 374, I have a couple of questions for you. One is, in this reaction profile, what are the reactants and what are the products? If you said the reactants are A and B and the products are C and D, you are correct. Good job. My second question is, what is the activation energy? If you said the activation energy is here, EA, and it looks like 25 to 70, so 45 kilojoules, you would be correct. Third question, what is the change in enthalpy? If you said the change in enthalpy is right here from the products, the enthalpy of the products minus the enthalpy of the reactants, you would be correct. It looks like about 10 to 25, so about 15 kilojoules. And the fourth question is this reaction endothermic or exothermic? If you said this reaction is exothermic, you would be correct because it's giving off energy. These products are at a lower energy state than the reactants, so you had to give off energy. Looking at the reaction profile on the next page, the same question, what are the reactants and what are the products? If you said the reactants are C and D and the products are A and B, you would be correct. And what is the activation energy? If you said this is the activation energy, so between 10 and 70 or 60 kilojoules, you would be correct. And then what is the change in enthalpy? If you said the change in enthalpy is right here, and it is 10 and 25, so 15 kilojoules, you would be correct. And just to clarify on the other one, the change in enthalpy was negative 15 kilojoules because we know it was exothermic. So this one is a positive 15 kilojoules. And then another question is this reaction endothermic or exothermic? If you said endothermic, you would be correct. It is taking in energy. As we can see, the products are at a higher energy state than the reactant, so it takes in 15 kilojoules of energy. And that concludes our notes for Chapter 12, Section 1. Good job! See you next time.